Ok, siamo partiti. Ok, quindi iniziamo la lezione adesso. So let me start with this slide where we just summarize the main results of the yesterday lesson. So this is the way we express the total energy in special relativity. So it's gamma mc squared, where gamma is the Lorentz factor. And you know this we can also express as the square root of squared momentum and squared mass. And then in general, the total energy is given by the sum of the kinetic energy and the rest mass energy. So the rest mass energy is brought here, so it's just E equal mc squared. And so you can obtain the kinetic energy just by difference. Okay, so the total minus the mass term, and you get the kinetic energy. Then you also know that the momentum we can express in special relativity as gamma and beta c. And then we can play around with these two definitions to get some useful formulas which are actually useful to solve problems. So from here, for instance, we can extract gamma, which is given by E divided by mc squared. And here we can also put this full expression here and put the c squared outside and simplify the denominator. The beta we can extract from the momentum definition, which is P over gamma mc. And then we can multiply by c, numerator and denominator, and so we get the total energy of the denominator. And then you can also take the product of the two, and you get this gamma beta is equal to P over mc. And then finally, we also derive the mass shell relation, where the square modulus of the form momentum is given by the square of the mass, essentially, and the invariant mass for a system of n particles, okay, which is the square root of the total energy squared minus the total free momentum squared. Mi fermo un attimo, chiedo ancora una volta un feedback, riuscite a sentirmi, a seguirmi bene anche con l'inglese?
Sì, sì.
Ok. Okay, now let's move on. Okay, so let's start now the new part. And we define now these three very important Lorentz invariants, which are called the Mandelstam invariants. So suppose we have a reaction, such this one, A plus B, that goes into C plus D. And so we can define these four Lorentz invariants. S is given by the sum of the two four momenta of the either initial state or final state particle squared. T is the difference between PA and PC or PB and PD, and U is the other complementary difference, PA minus PD and PD minus PC. Okay, so where each of these P is now the four momentum. Okay, it's not three momentum, but four momentum. Now, we will make quite some use of these variables, and especially for the first one, which is the most important probably. So the variable S actually corresponds to the squared of the total energy in the central mass. Okay, so square root of S is exactly the same as the energy in the central mass. We will use both to say the same thing. Okay, and this we will derive in a moment. And then variables T and U, which are those two here, correspond actually to the squared transferred for momenta. And this we will already make use of when we discuss the Feynman diagrams in QAD, for instance, or QCD. Okay. The three variables are not independent of each other. Okay, so one can easily show by using the mass shell relation that the sum of the three mass variables is given by the sum of the squared masses. Okay, so there is a relation that links the three. So only two of those are independent variables. The other you can extract from the relation here. Now, in general, when in the slide you see the symbol of the blackboard, that means that the continuous of the lesson goes into the blackboard. So now let me try to switch to the blackboard. Oh, so like this, no, like this. No, I have to do it here. Come faccio vedere qua? So, one moment. So, you still see, vedete ancora soltanto la slide, però, e poi soltanto me picco in basso?
Sì.
Ok, adesso non riesco ad andare più da questa parte mouse, quindi non riesco a switchare. Come faccio ad andare di qua? Scusate, devo capire questa cosa qui. Questo non mi dica un taglio. Io mi ho messo di qua.
Se adesso sei nella lavagna, professore, noi in teoria possiamo ingrandire la sua icona
Ah, ok, vabbè, ok, quindi potete farlo voi, non riesco a switchare tra le due monitor. Se riuscite a farlo voi, riuscite a mettere grande la parte della lavagna, possiamo continuare tranquillamente.
Sì, riusciamo a cambiarle noi.
Benissimo, ottimo ragazzi. Allora, datemi un attimo che prendo il materiale, do una pulita alla lavagna. Okay, so let's continue from here, and let's now describe the situation in the center of mass system. So suppose we have two colliding particles, A plus B, okay, and we want to calculate the center of mass energy, okay, for the system of two colliding particles. So in the center of mass, of course, by definition, the total momentum is zero. So this is given in general by the sum over the momenta of particles interacting in this case. Okay. And in our simple case, this is just PA star plus PB star. Right? Well, this asterisk is just to label that we are working in the center of mass system. Okay, so we will use this dimension here. Now, since all this has to be zero by definition in the center of mass system, that means that the P star A 3 vector must be opposite to the P star B vector. Alright? But then they are opposite as a vector, but moduli are the same. So we can also write that the modulus of the P star A is equal to the modulus of P star B, and we can simply call it modulus of P or just P. Now, let's work out the center of mass energy for this system. So we start using the S non-understand variable. And so this is by definition the sum of momenta plus EA plus EB in the center of mass all squared. Now, we use now the way we can express a square of a vector, essentially. So this is the zero component, so the energy, EA plus EB squared minus the sum of momenta, EA plus EB asterisk squared. Okay? Now we substitute what we have here, so we know already from here that since the sum has to be zero, this term automatically goes to zero. Okay, the center of mass. So we are just left with the sum of the total energies of the two particles squared. Okay, and since we are in the center of mass, this is nothing else than the center of mass energy squared. So our result is that the energy, the center of mass, which is the sum of the two energies in the center of mass, is just given by the square root of S. Is that clear? Okay. Now this is a generic reaction, E plus B. Let's make a specific case, which is actually very relevant. So suppose now the two particles are the same. So I need some more space here. Let me cancel something here. So let's now suppose that particle A and particle B are the same. In particular, suppose we are talking about two colliding protons. Suppose we have a collider, so we have one proton on one side, and proton on the other side, and they collide in the center of mass. So this is just the energy of each beam, okay, in a symmetric collider. Symmetric means that the two particles are the same, and also the energies are the same. So, for instance, like the Large Hadron Collider that we discussed yesterday, there are two beams circulating into the ring. One is both are proton rings, and both comes with the same beam energy. Okay, so this is exactly the situation of the Large Hadron Collider. And so, in this specific case, the center of mass energy, okay, which is square root of S, is just twice the energy of each big particle in the collider. Okay, and this we can further split it into twice the kinetic energy of the protons and the center mass plus the mass of the proton. Okay, so now the important message here is this one. So from here we learn that the center of mass energy is proportional to the beam energy in a symmetric collider. So if you want to double your center of mass energy, you just need to double your beam energy. okay, which from the technological point of view is not could not be triggered. If you want to double your energy in an accelerator, this is quite some effort because you have to change all the magnets and so on. But the important point is that if you want to double this, you just need to double the energy of the beam. And as we will see in a moment, this is not at all the case when we look for fixed target collisions. Okay, so let's now switch. Can I clear the board? Posso cancellare?
Sì, può cancellare.
Okay. Okay, let's now move to another case, which is now fixed target collision. Fixed target collision in the laboratory frame, not anymore in the central mass frame, but in the laboratory. Okay, so now the difference with respect to before is that now we have only one beam, suppose this is a particle A, colliding on a fixed target made by particle B. So the situation now is quite different. Let's write down the four momenta in this case for particle A and particle B. So by definition for momenta, the zero component is the energy of A, by C, and here we have the three momenta of particles A. Okay. And since particle A in our hypothesis is our beam particle, this we can also rewrite as E energy of the beam divided by C, and then momentum of the beam. Particle B instead is at rest. It is a fixed target experiment. So the form momentum, let me just drop this. The form momentum of particle B is simply, okay, in general is the total energy of B divided by C and momentum of B. But in practice, since B is at rest, the total energy is just the mass. So this is mB, and the momentum is 0. Because particle B is at rest. Okay, so there is not energy and not momentum. So once we define the two for momentum, we can again work out the central mass energy. So we start calculating the S minus some variable, which is as usual PA plus PB squared. So these two are as usual the two for momenta or particle B. And so now we use the definition. Okay, so it is EA plus PB squared minus the momenta of A plus the momenta of B squared. We substitute now our values on the line before. So this is energy of particle A plus mass of particle B squared minus, and here this is 0, okay, because the particle B is at rest, so we just have the modulus, the square modulus of the momentum of particle A. Now, instead of this, so this is energy of particle A squared plus twice mB energy plus mass of particle B squared minus squared, sorry, PA squared. Now we can collect this and this. So this is total energy of particle A squared minus total momentum of particle A squared plus twice mB PA plus mB squared. Riuscite a vedermi ancora?
Sì.
Sì, ok, perché mi si era chiuso il monitor. Vabbè. Okay, but now this definition is nothing less than the square of the mass of particle A. Okay? Just invert the energy momentum mass relation. So what you get here is ma squared plus mb squared plus twice energy of particle A mass of particle B. Let me write down this here because this is a quite important relation. So one of our results is that S is equal to ma squared plus mb squared plus twice energy of A mass of B. And now we can continue from here. because we can further split the total energy of particle A into kinetic energy and mass. So this is ma squared plus mv squared plus twice mv, and then this is split in kinetic energy plus mass of particle A. We take the products here, so we get ma squared plus mv squared plus 2 mv ka plus, sorry, let me do the other way around. So plus 2 ma mv plus 2 mv ka. And now you recognize that this is just a square of the norm, so this is nothing less than ma plus mv squared plus twice mv ka. And this is another major result that we write here, so this is also equal to, that we just call here, ma plus mv squared plus twice mv ka, where ka is the kinetic energy of the beam particle. Now, let's again make the hypothesis that the particles are the same. Okay, suppose now that particle A is equal to particle B. Suppose that this is a proton. Let's suppose that it's a proton. So now this relation here then becomes S is equal to, okay, sorry, let's take the square root of this. Energy in the center of mass is equal to square root of S, and then it is equal to square root of. Now the two particles are the same, they are both protons in the hypothesis, so this is twice the mass of the proton squared plus twice the mass of the proton and the kinetic energy of the proton beam, okay, in fixed target configuration. So F stands for fixed target. So this is okay. Now let's go back to this one. Okay, so the geometric relation that we found. So from here we can also derive that the energy in the center of mass, which is square root of S, is square root of ma squared plus mv squared plus twice aa mv. And this we can just call the beam energy. Okay, so this twice mv and then energy of the beam in the fixed target configuration. So these are the two main relations, okay, to express the energy in the center of mass, okay, in the case of fixed target beam. This is a special case for the two are just protons, not protons. But now the message I want to draw here is that suppose now we are in the ultra-relativistic regime, ultra-relativistic. That means that we can completely neglect the mass of the two particles compared to their total energy. Okay, so in the ultra-relativistic regime, we have Ma and Mv are much smaller than the energy. And so in this limit, we can neglect the two mass here. And the result that we obtain, which is the one we have to remember, is that now the center mass energy, okay, is approximately given by the square root of 2 mv beam in a fixed target, or if you want, the center mass energy is proportional to the square root of the beam energy in fixed target.
Prof, scusi, non riesco a capire cosa c'è scritto dall'apice di K.
Non riesco a sentirti, parla un po' più forte.
Non riesco a capire cos'è l'apice di K nella prima espressione riquadrata.
L'apice di K, questo qui?
Sì, esatto.
allora, in basso ho messo beam, quindi
Ok.
l'energia cinetica del fascio, sopra è fissa per fixed target.
Grazie.
Okay, so the result that we got is now in the fixed target scenario. The central mass energy is the square root of the beam energy. So now, if you want to double the square root, if you want to double the central mass energy, you have to multiply by a factor of 4 the beam energy. Okay, so it's quite substantial. For the collider, if you remember, we have seen that central mass is instead proportional to the beam. Okay, for the collider. No. Okay. So in order to get the same central mass energy, you need to have much more energy in the beam, in the case of fixed target experiment. Can any of you tell me why? Think a little bit and try to answer. So why do we need much more energy of the beam in order to get the same energy in central mass, in the case of fixed target compared to collider modes? Any guess? Avete capito la domanda? La domanda è perché in caso di esperimenti a bersaglio fisso, per ottenere la stessa energia nel centro di massa abbiamo bisogno di un'energia molto più grande.
Prof, un ragazzo le ha risposto in chat.
Ah, no, ragazzi, io non riesco a vederlo da qui, perché ci sono due fasci contropropaganti, e nell'altro caso solo uno. Ok, contropropaganti è fantastico. Sì e no. Allora, in realtà la questione è un po' diversa. Se voi avete, se voi avete un collider, per esempio immaginate l'H5, diamo un fascio di protoni da un lato e un fascio di protoni dall'altro lato, e diamo due fasci di particelle uguali e due energie di fascio uguali, ok? Il centro di massa è fermo nel sistema del laboratorio, perché tutto avviene nel centro di massa. Se invece avete un bersaglio fisso che un fascio che gli va addosso, okay, il centro di massa di questa reazione verrà boostato, okay, nel sistema del laboratorio. Perché si tratta di una collisione asimmetrica, una è ferma, la si muove, mentre nell'altro caso tutti si muovono in senso opposto. Okay? Quindi nel caso di collider il centro di massa è fisso, nel caso invece, quindi tutta l'energia disponibile nella reazione se ne va nell'energia del centro di massa. Nel caso di un bersaglio fisso, il centro di massa della collisione viene boostato, okay, nella direzione del fascio, quindi solo una parte dell'energia disponibile diventa fruibile nel centro di massa. Tutta la restante parte diventa energia cosiddetta non utilizzabile perché se ne va nel moto del centro di massa del sistema del laboratorio. Okay? Quindi, e questa è tipicamente anche la differenza diciamo, di scelta che si fa tra un esperimento a bersaglio fisso e un esperimento a collider. Se uno vuole massimizzare l'energia nel centro di massa, per esempio per scoprire particelle più pesanti, per esempio il bosone X, allora, è sparito qua il monitor, ok. Allora per massimizzare l'energia del centro di massa, allora conviene lavorare con il collider, perché tutta l'energia della collisione è disponibile per la reazione al centro di massa. Nel caso di bersaglio fisso, una parte dell'energia sarà disponibile per la reazione al centro di massa, ma una grossa parte va sprecata per il modo del centro di massa del laboratorio. Ok? È chiaro, ragazzi?
Tutto chiaro.
Ok. Ok. Qui faccio un po' fatica a leggere la chat, quindi provate a rispondermi a voce e poi mutate il microfono. Benissimo, allora andiamo avanti adesso e proviamo adesso a mettere insieme le due cose, vediamo come le due cose si correggono una con l'altra. Okay, so we saw that the central mass energy we can write as square root of mA squared plus mB squared plus twice mB, and then the energy of the beam in fixed target collision. But we also learned that we can express the central mass energy, we can express as twice the beam energy in a collider, in a symmetric collider. Okay? Symmetric means again the same particles, the two beams, and also same energy momentum. Okay. So this is for the fixed target, and this is for the collider. Now, suppose now that the particles are again the same, so MA is equal to MB, let's just call this M. Let's now try to find a relation, a more clear relation between these two. So from the first one, we take the square of this, so we take 2m squared plus 2m e beam fixed target, and then this must be equal to 4 times e beam collider squared. And so we can now see out this one here. So e beam on the fixed target, okay, will be given by twice e beam on the collider squared divided by m minus m, or physical relations that is the center of mass energy squared divided by 2m minus m. And now to conclude, if we avoid the ultra-relativistic regime, that means that the energy in the center of mass is much, much greater than the mass. Of course, we can draw these two mass down here in the relativistic limit, and so at the end you can write E beam on the fixed target configuration is approximately center of mass squared divided by 2m, or theoretically s divided by 2m. Momento. Okay. Now, in the slide that I already download on the web page, upload on the website, you find already a summary of all these stuff here. Let's now move on to the concept of threshold energy. All right. So suppose you have a reaction, a generic reaction, A plus B, that goes into C1 plus C2 plus whatever Cn. Okay. So it's a generic multi-body reaction. Okay. Now the center of mass energy in the laboratory frame. So the center of mass energy in the laboratory frame, we can write as for the initial state square root of Si, where I stands for initial state, and this is, as we know already, Ma plus Mb squared plus twice Mbka. Okay, now we have the center of mass energy, okay, for the final state in the center mass frame, for the final state, and this will be, okay, let's take a limit here, square root of Sf star. So F is for final state, and star is because we are now in the center mass frame, okay? And so this is the definition, the sum of all final state particle energies in the center of mass. Okay, so it's the sum of F that goes 1 to n of all the energy in the center of mass system. This we can further split into a mass term and a kinetic term as usual. So F equals 1 to n of K F, the center of mass system, plus M F. Now, of course, these two have to be the same because of energy momentum conservation and because of Lorentz invariance. So clearly, Si this has to be equal to Sf star. Both are, we can call S, and both are the square of the center of mass energy. Okay, these are so S is a Lorentz invariant, so it's the same in any frame. So it must be the same in the laboratory frame and in the center mass frame. Okay, so we can now equate these two versions. We get Ma plus Mv squared plus twice Nv Ka equal to the sum for F that goes 1 to n of Kf star plus Mf all squared. And so we can now extract the kinetic energy of the beam for one of the particles, so Ka is equal to sum F equals 1 to n of Kf star plus Mf all squared minus Na plus Mb squared divided by twice Mb. So all this, the hypothesis that we are working a fixed target experiment with the progressive fixed target. Okay. So this is the kinetic energy of the beam particle, okay, in the fixed target system. Now let me define you the threshold energy for any reaction. Okay. So the threshold energy for any reaction of this kind is the minimal kinetic energy of the beam that allows the reaction to occur. That means is the minimal value of Ka corresponding therefore to the situation where the final state particles are produced at rest, so without kinetic energy. Okay. So the minimal energy of the beam is the one that allows the reaction, but with final state particle produced at rest without kinetic energy. So now, on this after this definition that we also find in the slide that I provide you on the web, okay, we can redefine now the S at the threshold, okay, the threshold energy. And this, once we drop the kinetic energy in the final state, is just simply the sum for F equals 1 to n over the final state particle masses all squared. Okay? And so when we substitute now this into this, we obtain the threshold energy as I was defining before. Okay, so this is just given by the sum of F equals 1 to n over the mass of the final state squared minus Ma plus Mb squared divided by twice Mb, or this is just the S at the threshold minus Ma plus Mb squared divided by twice Mb. And this is what we call the threshold energy, okay, for a fixed target reaction. Is it clear? In case the beam energy is, of course, higher than this, the reaction will occur, and the final particle state, the final particle will also have some kinetic energy. Okay? If we take the minimum, that means the threshold value, the final particle are produced at rest, so only have the mass value. Chiaro ragazzi?
Sì.
Sì, è abbastanza chiaro.
Benissimo. Okay. Now, let's move to the last concept, and then we will solve some problems. Last thing I want to discuss is about two-body decays. Posso cancellare anche questa?
Per me sì. Per me sì, grazie.
Ok. Allora, intanto c'è un progresso, anche il connesso. Okay, so far we have discussed about reactions, A plus B that goes into something. Let's now discuss about particle decays. So suppose we have a particle A decaying into a particle B plus a particle C. Now, of course, in the center of mass system, particle A is at rest, and the two particles, the constant particles, are rated with opposite free momenta, because the total free momentum in the center of mass has to be zero, of course. So this will be momentum of particle B in the center of mass, and this is opposite the momentum of particle A in the center, particle C in the center of mass. Okay. And now again, the two are opposite, so momentum of particle B is equal and opposite to momentum of particle C, and the moduli are the same. So modulus of P E star is equal to modulus of P A star, which is equal to we can just call it P. Now let's consider first a simple case. It is the case where the two particles B and C are the same. Okay. So if B is equal to C, we have a simple scenario, and one example is the decay of the pi-zero meson into two photons. Okay. So the final state particles are the same. Okay. So in this case, the energy in the central mass of particle B will be equal to the energy in the central mass of particle C, and each of the two is just half of the energy available in the decay. Okay, and this is of course square root of s divided by 2. But in initial state, square root of s is nothing less than the mass of particle A. Okay, this is what we have. So in a very specific case where the two final state particles are the same, okay, then the energy of the particles will just be given by the energy in the central mass divided by 2. They exactly share half of the energy available in the decay. And energy available is nothing less than the mass of particle A. We don't have a kinetic term because in the central mass A is at rest. Okay? So this is, say, the specific case where the particles are equal. Let's now discuss the more general case where B is different than C. Okay. So we are now in the case where B is different than C, and we start calculating our S Mandel standard level as usual. So we know that this must be equal to the total energy available in the decay, which can only be the square mass of the mother particle. Okay, and it now by definition this is 4 momentum of B plus 4 momentum of C squared, and so this is energy of particle B plus energy of particle C in the central mass squared minus momentum of particle B in the central mass plus momentum of particle C in the central mass squared. And now these two are opposite, so we don't have this term here. And so this is nothing else than EB star squared plus EC star squared plus twice EB star EC star. Now we make use of the relativistic relation between energy, momentum, and mass. Okay, so each of these two terms is just a square momentum. So P B star squared plus the mass term and squared, and this is the first. Now the same is the same. So this will be P star squared C plus MC squared. Then we have the last term, which we can also rewrite in a different way. This we can write as E twice EB star. And then we can express the energy of particle C in terms of the energy of particle B because of energy conservation, of course, in the process. So it is nothing less than the total energy minus the energy of particle B in the central mass. Alright, so we are now expressing the particle C in terms of the particle B energy. Okay. Now this we can now develop. So this will be mB squared plus the square is here. MC squared, okay, this. Then we have to sum up the squared moduli of momenta, which are the same. Okay, just the number moduli are the same, they are just opposite in direction. So this is plus, suppose, twice PB star squared. And then we have these last two terms, so this is twice E star B square root of S minus twice E star B squared. Now we collect this and this. So we're going to have mB squared plus mC squared minus 2 EB star squared minus PB star squared plus twice EB star square root of S. And this, you now recognize, is nothing less than the square mass of particle B. Okay, so we have mv squared minus twice mv squared. So this results mc squared minus mv squared plus twice E star in the square root of S, as we here, and E star B. And all these, we start from S, so all these must be equal to S. We are almost done. So now what we want here is single out the central mass energy of particle B. So E star B from here is just S plus mb squared minus mc squared divided by twice square root of S. Square root of S in decay is nothing less than the square mass of the mother particle. So this we can also write as ma squared plus mb squared minus mc squared twice ma. Okay, so we can express now the central mass energy of particle B in terms of the masses, okay, of the mother particle and the decay products in this simple way. Now, in our derivation, we wrote explicitly the energy of particle C in terms of energy of particle B. Of course, we can do the opposite, and thus with the same derivation, we would obtain, this you can check yourself, the energy of particle C in the center of mass will be given by S minus mv squared minus mc squared divided by twice square root of S. That is ma squared minus mv squared plus mc squared divided by twice ma. Okay. So these are the expression now of the central mass energy of particle B and C in the general case, where B and C are different. Of course, now if we assume that B is equal to A, okay, we get back to the original case. Okay, so these two go away, these two go away, and in both cases we end up with ma squared divided by twice ma, that is ma divided by 2, that is square root of S divided by 2. Okay, so these are the general formula, and if by chance the two particles are the same, you obtain the simple relation that we found before for the case such as, for instance, the pi 0 equal to gamma, okay, with the particles in the different state are the same. Tutto chiaro, ragazzi?
Sì, tutto chiaro. L'unica cosa direi che, cioè, mi sa che B uguale A dovrebbe essere B uguale a C, giusto?
Ripeti, scusa?
Dovrebbe essere B uguale a C per ottenere l'ultima espressione vista,
Sì,
giusto?
certo, scusa. Sì, le particelle hanno iniziato finale, grazie.
Ok, niente.
Ok, altri commenti, domande? Ok, facciamo una pausa
No,
di...
no.
Ok, se non avete domande facciamo una pausa di 5 minuti e poi svolgeremo alcuni problemi, ok?
Sì.
Vabbè, dai, 5 minuti di pausa. Ok, ci siete ragazzi?
Sì, sentito.
Ok, bene, bene, ok. Allora, un secondo. Allora, adesso ho raccolto qui 6-7 problemi, ricordate ovviamente che le slide che ho messo sul web. Prima di iniziare i problemi volevo chiedervi, le cose che abbiamo visto oggi le avete già studiate in altri corsi o è la prima volta che le vedete? Prima volta, ok. Mentre quelle di ieri immagino le avete già viste sicuramente, dai, almeno, ieri era proprio le basi, no? Perfetto, ok, va bene, grazie. Va bene. Allora, iniziamo col problema 1.2. So, for an experiment with colliding proton beams with energies much greater than the mass of the proton, derivate the expression of the center mass energy if the two beams are collinear, calculate the center mass energy for the case the two energy are 25 GeV, and calculate the beam energy for fixed target proton-proton collision at the same center of mass energy. Okay? So questo problema mette un po' insieme tutte, diciamo, le cose che abbiamo visto nella prima parte della lezione di oggi. Okay, so let's start with question A. Okay, so let's write down the expression of the four momenta of the two colliding particles. So P1 is P1 and P1. Okay, we work in natural units, so we put the C equal 1, okay? And P2 is P2, the momentum of particle 2. Okay, now we have all the ingredients to calculate the S number subvariable. So S is P1 plus P2 squared. That is P1 plus P2 squared minus P1 plus P2 squared. So we have not known squares, so this is P1 squares plus P2 squares plus twice P1, P2, and then we have minus P1 squares minus P2 squares minus twice P1 scalar product with P2. Now, as usual, we can collect this one with this one, and this one with this one. So this is P1 squared minus P1 squared plus P2 squared minus P2 squared. Then we have plus twice P1, P2, and then we can make explicit the scalar product as twice P1, P2 cos theta. Now we realize that these are the masses squared, so mass of particle 1 squared plus mass of particle 2 squared plus twice P1, P2. And now we remember from the text that the two beams are collinear. Okay, collinear means that one comes in this way and the other comes in the opposite way. Okay, and that means that the angle theta is equal to pi, and so the cos theta is just -1. And so this we can just write as plus twice P1, P2. Now we remember from the text that it is a ultra-relativistic collision, okay, where the mass of the particle, which is a proton in this case, so the two are the same and are also proton mass, is much smaller than the energy, the center of mass, okay, the energy. So sure, okay, let's write this for the protons, in sense. Oh, okay. And proton 1, that's all squared, so this is twice mass of the protons, okay, plus twice Fp squared, plus, no, sorry, let's still work on the general case. We want to, at the end we make the special case, okay. So, okay, let's complete this first, and then we make the approximation at the end. So this m1 squared plus m2 squared, okay. Now, in the ultra-relativistic limit, okay, where we can actually neglect the masses, we also know that the energy is essentially equal to the momentum, okay. So we can write this as 4 times E1, E2, and neglect the two mass. And then we can just put the approximate equal. So in ultra-relativistic limit, we can neglect the mass compared to the energy, but also the energy is essentially given by the momentum because the mass is negligible. Okay. So our result is that the center of mass energy, which is square root of s, is given by square root of 4 E1 E2 or 2 square root of E1 E2. Okay, so this is the derivation that was required by in point A. In point B, we just make a calculation. So in point B, we know that E1 is equal to E2. So this is a general case. Now we go to the specific. So E1 is equal to E2 and is equal to 25 GeV. Okay, so the central mass is twice square root of E squared, that is twice square root of 25 GeV squared, that is 50 GeV. Okay, so this is the result for a symmetric collider, proton-proton collider, or whatever particle they are. So same particle and same opposite momentum. Now let's move to point C, okay, which require us to calculate the beam energy for a fixed target proton-proton collision, but with the same center of mass energy. Okay. So let me write down the result here. So for the collider mode, the energy in the center of mass is only 60 GeV. For the rest, we can now cancel. Now, point B, point C. So now we are dealing with a fixed target proton-proton collision. Okay, so the formula will be the following. So for the beam particle, this will be E1 and P1, or we can just call energy of the proton and then momentum of the proton. And for particle 2, the proton is at rest, so this is just the mass of the proton and 0 the momentum. It's a fixed target, okay? So the only energy available is the mass. There is no momentum here. And so again, we calculate the S Anderson as E1 plus E2 squared. That is E1 or EP plus MP squared minus EP squared. This is EP squared plus MP squared plus twice MP EP minus EP squared. Now you know we can collect these two. So this is EP squared minus EP squared plus MP plus twice MP energy of the proton. Again, this is the square mass of the proton, so this is twice MP squared plus twice MP EP. Okay, and in the ultra-relativistic regime, okay, you can neglect the mass compared to the energy. So essentially what we found is that the central mass that S is approximately equal to twice mass of the proton energy of the proton beam. And so the energy of the proton beam will be given by S divided by twice the mass of the proton. And since we want to calculate these at the same center of mass energy as before, okay, So we know already that this is 50 GeV. So this is 50 GeV squared divided by twice mass of the proton, which is how much is the mass of the proton in GeV? You tell me?
One GeV.
Approximately 1 GeV, a little bit less. So it's 0.938 GeV. Okay? So if you do now this ratio, you obtain a huge value, 1333 GeV. And this you have to compare with 50 GeV in the target mode. So this is a fixed target mode, okay? And the reason for that is what I was telling you before, okay? So if you want to obtain the same center mass energy with a fixed target experiment, your beam energy must be much, much higher than the collider mode. And the reason for that is that a big fraction of the energy in the collision is wasted for the motion of the center of mass into the laboratory frame. And only a small part will be available for the reaction itself. Alright? Ok. Se non ci sono domande su questo, andiamo al successivo. Ok, allora il problema 1.3. A proton beam with momentum 100 GeV over C hits a fixed hydrogen target, so essentially a fixed proton. Okay? Calculate the center of mass energy for this interaction, and then what beam energy would be required to achieve the same center of mass energy in a symmetric proton-proton collider. So this is, let's say, the opposite problem. Look at this. Okay, so we have a beam with momentum of 100 GeV over C. Okay. What we want to know is the total energy of the proton in a fixed target collision, and then we apply the standard relativity relation that is E squared plus mH squared. Okay. So this is 100 GeV over C squared plus approximately 1 GeV, okay, so be correctly, 138 GeV squared. Okay, but then you recognize that this is completely negligible compared to this. Okay, so this is essentially still 100 GeV. That means it is essentially equal to the momentum of the proton. All right. So now we use our result. We don't have to derivate more. So we know that square root of S, okay, is given by twice mp energy of the proton in fixed target. This is approximately equal, okay. And so we have square root of twice times 0.938 GeV times 100 GeV. And the result is about 13.7 GeV. This is the center of mass energy for this accelerated process. Okay. Now the second question is what beam energy would be required to achieve the same center of mass energy, but now in a symmetric proton-proton collider. Okay, so we know that for a symmetric proton-proton collider, root of S is twice the collider. This we derived 1 hour ago. Okay, and so what we need here is that P collider is equal to twice, square root of S divided by 2. Square root of S is the center of mass energy that we know already. So it is 13.7 GeV divided by 2, and this is just 6.8 GeV. So again, we observe the same features. Okay, if you want to have the same center of mass energy, you need a much smaller energy in the collider mode compared to the fixed target mode. Okay. Okay, let's now move to the next problem. Okay, here there is some text to read, so let me go through the text. So at SLAC, which is the Stanford Linear Accelerator Center in California, an asymmetric collider was operating with an electron beam of 9.06 GeV and a positron beam, that is the antiparticle of the electron, of energy 3.11 GeV. Now, with these specific energies, the center of mass energy corresponds to the mass of the particle, which is the epsilon 4s meson. And this is essentially an excited bound state of bottom-antibottom quarks. Okay, we will study this. Which then decays immediately into a pair of B mesons. So B0 anti-B0 is a meson anti-meson. Okay? B is a heavy meson with one B quark and one, so the B0 is one B bottom quark and one down quark. And then particle is the opposite. Okay? Now, due to the different beam energies, okay, so the energy of the electron is essentially 3 times larger than that of the positron. What happens is that the produced epsilon meson is not at rest, as it would be in a symmetric collider with the same central mass energy, but instead it is boosted along the direction of the most energetic beam, which is the electron beam. So in a sense, an asymmetric collider is something in between, something between a fixed target experiment and the collider experiment. Okay, you see, part of the energy goes into the center of mass of the reaction, but part goes to the motion of the center of mass into the laboratory. So it's halfway between the fixed target experiment and the collider experiment. So we were saying that due to different energies, the epsilon meson is boosted along the direction of the most energetic beam, which is the electron beam. As a consequence, the two B0 mesons, so B0, B bar 0, will travel a certain distance in the direction of the electron beam before decaying, and the decay occurs with a decay time of 10 to the minus 12 seconds, which is typical of weak processes. This is a decay regulated by the weak interaction. And so since they travel for a certain instant, it is possible to reconstruct their decay vertices with, for instance, a high resolution tracking detector, okay? One of those that we discussed yesterday, for instance. Instead, if the epsilon meson were produced at rest, so in case of a symmetric collider, the energy of the two B mesons would be too small to cover a measurable distance before decaying. Okay, and their decay vertices would not be possible to be resolved experimentally. Okay, so is it clear?
Yes. Yes.
Okay, great. Okay, now let's go to the problem. So there are four questions. First one is the energy in the center of mass for this asymmetric collider, the velocity of the center of mass relative to the laboratory frame, the beam energy of positrons and electrons corresponding to the same value of the center of mass energy, but in a symmetric collider, and the energy of the positron beam corresponding to the same value of the center of mass energy, but now with a fixed electron target, suppose an atomic electron. Okay, so this is a quite very complete problem. Okay, so let's start with first answer, which is about the energy in the center of mass. Okay, so what we have, actually just a lot. Okay, so in the laboratory frame, we have the 4 momentum of the electron that we call P minus. Okay, is given by P minus and 3 momentum of the electron. And the 4 momentum of the positron that we call P plus is equal to P plus P plus. Now we calculate as usual the S minus and variable. So this is P minus plus P plus squared. And so now we substitute. This is P minus plus P plus squared minus P minus plus P plus squared. This, as usual, P minus squared plus P plus squared plus twice P minus P plus minus P minus squared minus P plus squared minus twice P minus P plus. Okay, so we know now that this crossroad we can write as P minus P plus cosine of pi. And the reason for that is that Stanford is a linear collider. Okay, so we have a beam from this direction, say the electron beam, and a beam from the positive in the other direction. Okay, and so again the angle is pi. Okay, so this goes now. We get a minus sign here. So what we get here is that we collect E minus plus minus E minus squared plus E plus squared minus E plus squared as usual. So we are collecting now these plus twice E minus plus, and then we plus here twice E minus plus. This is mass of the electron square. This is the mass of the photon square, which is just the same. Electron and photon have the same mass, because it's just one behind the half of the other. Okay? And we can then have plus, now, of course, we can completely neglect the mass of electron and photon compared to the beam energy that we have. So we are, of course, in ultra-relativistic regime. And so we can also equate the energy momentum. So this is approximately equal to 4 times E minus E plus. So the center of mass energy, okay, which will be given by mass of epsilon. Will be 4 times E minus E plus. So it will be 4 times 9.06 GeV times 3.11 GeV. And this results 10.58 GeV, which is in fact the mass of the epsilon 4s meson. Okay. Now let's move to the point B. So now is the velocity of the center of mass frame relatively to the laboratory frame. Okay, so let me remind you that we can always write in special relativity momentum as gamma and beta c. Okay, this is a general formula. So in our case, okay, the momentum of the epsilon, okay, which is the modulus of the momentum vector of epsilon, is given by gamma of the epsilon, the mass of the epsilon, beta of the epsilon, and speed of light. Now remember again that as light is not a linear collider, it's too big to collide from opposite directions. Okay. So this is given by, in general, modulus of minus plus the modulus of E plus. This will be the total momentum. And now, suppose that this is the z axis, so we can also use here the unit vector k. Over here. We have here just to indicate the direction of the beam axis. And so, to make this formally correct, we can write this vector we can write as PE in the z-axis direction, and then we have plus E plus in the opposite direction. And so we have PE minus E plus, and this is the modulus of this vector. And so when we take the modulus, we don't care anymore about the direction. So this is just make it simple, P minus minus P plus. And since we can neglect now the mass of the electron, this is approximately equal to E minus E plus. And so we can substitute now the values. So it's 9.06 GeV minus 3.11 GeV. So let's call this. This turned out to be 5.95 GeV. Now to make it formally correct on the units, okay, we are still talking about momentum. Now the numerical value are the same of the energy. So to be correct, we have to put like the C here. Okay? Now we do the same exercise for the total energy. So the total energy of the epsilon is gamma of the epsilon, the mass of the epsilon, and C squared. So we are using the general relation E is equal to gamma and C squared. And this is again the total energy. So this is E minus plus E plus, which is 9.06 plus 3.11 GeV, that is 12.17 GeV. So now we have momentum of the epsilon and the energy of the epsilon, and we can play around with the relativistic relations, okay? So we know that the beta of the epsilon, okay, that corresponds to the beta of the central mass into the laboratory frame, because the epsilon, once you create the epsilon in the collision, the epsilon will move with a certain velocity in the laboratory frame, and we have to calculate the velocity now. So, according to the formula that I gave you before, this is P of the epsilon divided by gamma of the epsilon, mass of the epsilon, and C. We multiply by C, so it's momentum of epsilon, times C divided by gamma of the epsilon, mass of epsilon, and C squared. This is P of the epsilon C divided by the energy of the epsilon. And so we just need to put the numbers. I leave it here. So beta of the epsilon is P times C divided by P of epsilon, and I will substitute the numbers. So we have 5.95 GeV over C times C divided by 12.17 GeV. No. So actually this is 0.49. So this is the beta of the produced epsilon, but beta is nothing less than B over C, and so at the end we obtain velocity of the epsilon in the laboratory frame, which corresponds to the velocity of the center mass of the collision in the laboratory frame, and this is just 0.49 times the speed of light. Now, the next question is the Levy energy of positons and electrons corresponding to the same value as their mass, but now in a symmetric collider. So we know the formula, square root of S for this expression C. So the S is, for a symmetric collider, is twice the beam energy, okay? And so the beam energy is square root of S divided by 2, that is 10.58 GeV divided by 2, that is 5.3 GeV. So in order to form epsilon for S meson in a pure symmetric collider, you need both beam of 5.3 GeV. Okay, but then in this case, the epsilon meson will be produced at rest, because in a symmetric collider, the central mass is at rest. Okay, and now the last one. So the last question is the energy of the positron beam corresponding to the same value of the center of mass energy, but now with a fixed target electron, so suppose an atomic electron. Okay. Of course, an atomic electron clearly is never at rest, you know, but here we can neglect its kinetic energy compared to the energy we have here. So we're talking about 10, 9 something kg. Okay, so we can assume with a very good precision that the atomic electron is at rest in this context. Okay, so now we go to the last question, E. We can go directly to the formula, we don't have to derivate anymore. So we know that the center of mass energy for this target is approximately twice mE, and then we have the beam energy. So it's the target case. Okay, and so the beam energy in the fixed target mode is the center of mass energy squared divided by twice the mass of the electron. Since we are working with the same center of mass energy as we are required by the text, this is still 10.58 GeV squared. And then you know the mass of the electron is very tiny, it's 0.511 10 to the minus 3 GeV, so just a half MeV. And so the calculation we find 1.1 10 to the 5 GeV, which corresponds to 110 TeV. Okay. So once more, we are in the case that if you want to obtain the same energy, center of mass energy, okay, the same energy in the center of mass, but now with a fixed target experiment, you need the beam energy to be extremely high. Okay. So compare 110 eV with something in the order of a few GeV. Again, for the same reason. Okay. Here, questions?
It's quite clear.
Ok, benissimo, grazie. Okay, let's move on to the other problem. So consider the two-body decay. So now we switch to decays. Consider the two-body decay delta plus into pi0 proton with the mass of the delta plus is in here. Determine energy and momentum of the two final state particles in the central mass system. Okay. So let me clear the blackboard. Okay, so what we're going to study is this decay, the lambda plus, the delta plus goes to the 0 proton. Okay, the delta plus, okay, this we will study later on in the course when we talk about hadrons. You can imagine the delta plus as an excited state of the proton. Okay, so it essentially decays strongly. Okay, in this way, in pi 0 and the proton. So in the center of mass, our delta plus is at rest, and the proton and the ions are emitted back to back with opposite momenta in the center of mass. That means that the total momentum in the center of mass must be 0, and so that the momentum of the 0 must be equal and opposite to the momentum of the proton, and the two in the module must be the same, must have the same modulus, that we can simply call P. Now, the full momentum is the initial state where we only have the delta plus at rest. So this is in general E star, P star I, sorry. And since we are at rest, this is nothing else than the mass of the delta plus and 0 momentum. In the final state, we have now two particles. So we have E star F, P star F, okay, that we can develop as E star by 0 plus E star proton, and then the momenta, which are P star by 0 plus P star proton. But we know already that in the center of mass the total momentum is 0, okay, so this guy goes to 0. So if we want to calculate our momentum variable as F, okay, which is P pi plus P proton squared, okay, this would be just given by P by 0 star plus E proton star squared. Now we will not derive this anymore. We already did on the theory. Okay, and let me just go to the results that we derived before. So the S number is a variable, which of course must be equal in the initial and the final state because of energy momentum conservation. We can write in two ways. So the first one is S squared proton minus M by 0 proton squared plus twice square root of S and E star by 0. If we explicit the function of the zero energy, or we can also explicit as a function of the momentum, the proton energy. So this is also given as m by 0 squared minus m of the proton squared plus 2 square root of s, and now we have the energy of the proton in the center of mass. Okay? Depending on which variable you are making explicit here. And this, by energy momentum conservation, must be equal to the square mass of the mother particles or the delta plus particle. That is the only energy or the full energy we have in the initial state. Okay. So now given this, we just need to put the numbers. And so for the y 0, this will be given by S minus mass of the proton square plus mass of the y 0 squared divided by twice square root of s. That is the mass of the delta plus square minus mass of the proton square plus the mass of the y 0 square divided by twice the mass of the delta plus. Let's now substitute the numerical values. So the mass of the delta plus resonance is given by the text. It is 1232 MeV. Let's go for MeV squared. The mass of the proton, is 0.938. Oh, okay, we're going MeV, so 938 MeV squared. Do you know by chance the mass of the neutral pion?
No remember at all.
The order of magnitude, at least?
Some MeV,
A bit more.
100 MeV, something like this.
Yes, order of 100 MeV, you are correct. This will be starting in the course. So the exact value is 135 MeV. Times twice the mass of the delta. And this results in 266.3 MeV. So this is the energy in the center of mass of the by 0. And then we do the same exercise for the proton. So proton in the center of mass will be S minus m squared by 0 plus m squared of the proton divided by twice to the s. That is the mass square of the delta plus minus the mass square of the 0 plus the mass square of the proton divided by twice the mass of the delta plus. Let's put numbers. And the result is 965.7. Sorry, yes. MeV. Now, what actually the text wants is not only energy but also the momentum. And of course, in the center of mass, the modulus of the momentum is the same for the two. They are just opposite in direction. So I can easily show that P dot for the by 0 in the center of mass is equal to the P of the proton in the center of mass and this is then by either this direction, so e squared by 0 minus m squared by 0, or the same, also the proton. So e squared proton minus the mass of the proton, and both, of course, we give you the same value, which is 239.5 MeV over C. You can check yourself. Okay. Let's go on. 1.6. Consider the three-body decay K0 into P0 pi plus pi minus with the mass of the K0 provided here. Find the maximum and the minimum values of the P0 energy and momentum in the K0 rest frame. Okay, so in the center of mass frame, essentially. So the K0 is, we call it neutral kaon. Okay, so it's a meson made by a strange quark and a light quark. In this case, it's a strange quark and a down quark. So it is there's a neutral electric charge. And one of the main decay modes is in fact in 3 pions, by 0, by plus and by minus. Okay. So the difference with respect to before and to what we've studied so far is that this is a 3-body decay. Okay, so we have now 3 particles in the final state. And this, of course, makes things more complicated in general. So in the center of mass, we have our K0, okay, which is at rest. And then it means that this momentum of the 3 particles will be shared this way. So it will be the minus, the plus, and the 0. Of course, the total momentum in the center of mass must be 0. So we have S is equal to the mass square of the K0, which is 498 MeV squared. And then we have again the total momentum in the center of mass must be 0, that is the momentum of the 0 plus the momentum of the plus plus the momentum of the pi minus, and this must be 0 in the center of mass frame. Then we have the formal momentum initial state, which is Fi star, Ti star. And since in the initial state the K0 is at rest, okay, this is just given by the mass of the K0 and then 0 momentum. And then for the final state, we have Ef star, Ef star. And this we can make explicit for all the particles. So we have the energy of the pi plus the energy of the pi minus plus the energy of the K0, and then we have the vector sum of the momentum of the K0 plus the momentum of the pi minus plus the momentum of the K0. So these are our initial state and final state for momenta. Now, so the complication here is that we have 3 particles. Okay, so essentially they can share the total energy in infinite possible ways. Okay, this is the complication between a 3-body particle and a 2-body particle system. However, we are only asked to find the maximum and the minimum. Okay, and this makes things much easier. So, can any of you try to think in which case the pi0 gets the highest momentum? Which configuration? Try to think a little bit.
The other 2 particles are parallel with each other, but anti-parallel with this particular maybe.
Exactly, you're right. Okay. So the situation where the pi0 gets the maximum momentum is where the pi0 goes in this way, and the pi plus and the pi minus goes parallel the opposite way. Okay? But now this becomes easier because we can treat this as a 2-body decay. So we can consider the pi plus pi minus system has one single pseudo particle. And so we know how to solve this very specific case, right? So the energy of the pi0, maximal energy of the pi0, we use the same formula as the previous problem, but now considering these 2 particles as a single particle, it will be S minus m squared pi plus m squared pi minus plus m squared by 0 divided twice square root of s. And so we can substitute here. So S is the square of the mass, okay, of K0. So this is 498 MeV squared minus. This is twice the mass of the charged ion, which is just a little bit heavier than the neutron. The number is 135 MeV, and the charges are 140 MeV. Plus, so it goes squared, yeah. And then we have mass of the zero, which is 135 MeV squared, divided by twice the mass of the Km, 498 MeV. And the result of this is 189 MeV. And this is the energy and the momentum, the maximum momentum of the zero. Okay, we can usual way as the energy of the zero max squared minus the mass of the zero squared. And so this is square root of 189 GeV squared minus 135 MeV squared. And the result is 132.3 MeV. Or seems to be correct. Okay. So this is the first answer. The second, we are asking about the minimum energy and momentum of the pi zero. So can now anybody tell me in which configuration the pi zero gets the minimum energy, minimum momentum? Idea?
Maybe when the momentum of pi q and pi minus are opposite.
Exactly, correct. Because in this case, the pi plus and the pi minus share the full momentum of a variable, okay, and the pi zero is just at rest. Okay, so in this simple case, the energy of the pi zero min is zero, and also the momentum of the pi zero min is zero. It's a very special case, but of course this is one of the infinite possibilities, where the pi zero is at rest, and the other two, of course, have to have opposite momentum. Good. Clear to everybody?
Yes, thanks.
Okay, great. Now let's do the following. So the next problem, try to do yourself as an exercise, and we go now to the last problem, which is essentially an extension of the problem set. So the two are essentially very similar. So we solve only the 1.8. These problems are about the threshold energy. So that was one of the topics we started today. So consider the reaction proton-proton that goes into proton-proton pi zero, where the two incident protons have opposite momentum. Calculate the threshold energy for this reaction, and then if the proton is at least one proton is at rest, calculate the minimum Lorentz factor of the other proton that allows the reaction. Okay. So let me write down the reaction. So we have a collision between two protons that results in two protons plus 2 pi zero. Okay. Now, if you remember the threshold value of the Magnus variable, that means the value where the kinetic energy of the final state particles are zero, so they are produced at rest, is just given by the square sum of final state particles, masses. And so in the final state we have two protons and two pions, so this is twice the mass of the proton plus twice the mass of the ion squared. Now, let's work out the formula. Q1 is equal to P1, so we can just solve E and P. And P2 is P2, or it's just called P minus P. Okay? Because we know from the text that the protons have opposite momentum. Okay, so suppose it is a linear proton-proton collider. Okay? So now, S is equal to P1 plus P2 squared. And now, okay, so this is E plus E squared plus E minus E squared. And so this is just 4 times E squared. And for the reaction to occur, this must be equal or greater than the threshold. Okay. So now we can equate the two. So we have twice e to the square must be greater or equal to twice the mass of the proton plus twice the mass of the phi0 squared. So it turns out that the energy must be greater or equal than the mass of the proton plus mass of the phi0, that is 0.938 GeV plus 0.135 GeV, and that is 1073 GeV. Okay, so this value here is the threshold energy. If the beam energy is greater or equal than the threshold energy, then the reaction will occur. The threshold energy is the one where the final state particles are produced at rest. Okay.
Excuse me, I have a question.
Mm-hmm.
In the law, by the scusi, posso dirlo in italiano? Adesso non ho l'inglese prontissimo. Chiedo scusa. 4 al quadrato è maggiore o uguale di S? Non leggo cosa c'è scritto nel pedice.
Ah, scusi, S threshold, TH.
Ok, grazie.
Se S è maggiore di S threshold, la reazione può avvenire, ok? S threshold è il valore limite di S per cui la reazione avviene, ma i prodotti finali
certo.
non devono cambiare. Rispondiamo adesso all'ultimo punto, punto B. If the proton is at rest, calculate the minimum Lorentz gamma factor of the other proton. So adesso siamo nel caso di fixed target. Quindi la reazione rimane, the reaction remains the same, but now in fixed target configuration. So suppose this proton here is a fixed target, and this is the beam. Okay, so now the form momentum of particle 1 is energy and momentum. The form momentum of particle 2 is the mass of the proton and 0. We fix a target configuration. So S is equal to P1 plus P2 squared, that is E plus MP squared minus P squared, that is twice MP squared plus twice MP P. So in order for the reaction to occur, we still have to have S greater or equal to the threshold value. Okay, that means that this what we have here, so twice the square with mass of the proton plus twice MdE must be greater or equal to the threshold value. Okay, I delete that here in your notes. That was 2 MP plus 2 m by 0 squared. That is 4 times mass of the proton square plus 4 times mass of the phi square plus 8 times mass of the proton mass of the phi0. So we can now extract the energy here. This must be greater or equal to twice mg squared plus 4 m phi0 squared plus 8 mp and pi divided by twice mg. Okay, and this is the threshold energy. So the energy must be at least equal or even greater than the threshold energy. But now we remember, right here, we want to calculate now the Lorentz gamma factor. Okay, but we know how to do this because we know that in general E is equal to gamma mc squared. Okay, so in our case, the threshold value of gamma is equal to the threshold value of energy divided by the mass of the proton. Okay. And so we just need to substitute. So it will be twice the mass of the proton squared plus 4 times the mass of the ions square plus 8 times mass of the proton mass of the barium divided by twice the mass of the barium now squared. And this we can also write, okay, we can just put numbers here, or you can also write in a better way, like 1 plus twice m squared by 0 divided by m squared proton plus 4 times m by 0 divided by m proton. Now you just need to put the numbers. That is 1 plus twice 0.135 GeV squared, meaning 138 GeV squared plus 4 times 0.135 GeV divided by 0.138 GeV, and the result is 1.6 joule. Okay, so this is the minimal value of the Lorentz gamma factor in order for this reaction to occur. And minimal means the one that provides final state particle at rest. Okay?
Ok.
So try to solve the previous problem. It's just the same of the first part of this one. Okay? And basta, la lezione finisce. Ci vediamo noi mercoledì. Quindi adesso abbiamo completato il modulo 1, che di fatto era questi richiami, in realtà una parte un po' nuova per voi di kinematica relativistica. Cominceremo mercoledì invece con la parte di regola della questione di l'urto, dei eventi. Ok.
Ok.
Arrivederci.
Professore,
Sì, sono domande?
ha caricato le slide di oggi sul sito?
Quelle di oggi sono sul sito, le caricate ieri. Nei prossimi giorni caricherò quelle della prossima lezione, troverete quelle della prossima lezione.
Va bene, grazie. Buona giornata.
Arrivederci.
Sì.